Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let me introduce Paul Rowe from all the way from Australia. And I believe in very short introductions. And I think he can read the title probably better than I can and introduce where he's from. So without further ado, let me hand over to Paul. Thank you, Paul.
Thank you, Stuart. Yes, thanks everyone. I'm Paul Rowe. I'm from Brisbane in Australia, from QUT, Queensland University of Technology. And I want to talk to you today about a project that I've been involved in for the past couple of years about acoustic sensing, using acoustics to monitor the environment. So I'll start by giving a bit of motivation. I'll talk about some of the sort of the challenges, briefly touch on some of the sort of the architecture, IT stuff, and a couple of projects. And if hopefully we've got time, I'll do some demos too. Okay, I should say this is joint work with some of my colleagues also, all at sort of QUT. There's a mixture of computer scientists and ecologists and people who are better mathematicians than I am. So in some ways I'm probably the least qualified person to give this talk because I'm neither an ecologist nor am I a sort of signal processing expert. Anyway.
You're amongst friends.
I'm amongst friends. Amongst friends. So when I talk to some of my ecologist colleagues, they talk about ecosystem services. So this is sort of part of the new way of considering kind of the Earth. It's a sort of a systems point of view. The Earth provides us with these sort of services, water, food, energy. And in exchange, we obviously sort of interact with the Earth and impact upon the Earth. And so in particular, as we sort of heard this morning, there are sort of issues of grave concern like kind of global warming, pollution, overpopulation, land use change, biosecurity threats, and things like that. One of the key things about kind of looking at ecology and environmental health is that you need to better manage things. So in order to better manage things, you first of all need to better sort of measure them. So I'm interested in working with ecologists to use computer technology to better sort of measure the health of the environment, although the ecologists don't like the word health sort of too much. I'm lucky, originally from the UK, I live in Australia now. Australia's a beautiful country. Please come and visit. We've got the IEEE eScience conference there next year, in December next year. It's considered to be sort of mega diverse, and by that it means that there's an awful lot of species which are only endemic to Australia. Obviously sort of things like kind of kangaroos, marsupials, many other things. Unfortunately, Australia's also seen severe declines in a lot of populations of animals and and marsupial species and things, which is obviously a big issue, and it's also been shown to be particularly at risk from even sort of moderate climate change. In order to sort of assess ecological health, there's a sort of general movement now towards sort of assessment tools, towards sort of calibrated assessment tools. Within Australia, unfortunately, each state seems to have its own tool, although they are talking to one another at least, which they don't do about everything. One of the tools, the tool that they use in Queensland in particular, is one known as sort of biocondition. This is a calibrated vegetation assessment tool that starts off with some sort of remote sensing and some geological information and things to sort of get an overall sort of picture of the environment. The rest of it is done through sort of on-the-ground surveys. Now this is at the moment, the sort of calibrated tool is just a vegetation assessment tool, but they're moving towards fauna surveys too, and we've been working with these guys to look at whether essentially we can use acoustics for measuring biodiversity. The problem with the kind of current method of operation really is just one of scale, that it's just very labour intensive. It involves teams of ecologists going out into the environment and taking kind of samples, taking kind of observations. In Australia, like the US, is sort of a large country. We can't get a good overall picture on environmental health in that way. So the idea that we and other people have had is of using kind of sound as a way of sort of scaling the kind of observations that we can make. I'll just play you some brief sound. So this was from one of my colleagues sort of heard and recorded just a couple of days ago, where he lives. There's some interesting birds there. There are some parrots. That's a whipbird. There's some rail and a few other things going on there. So kind of our goal, in a sense, is to sort of emulate the scientist's sort of eyes and ears. Those are parrots. So the kind of things that we'd like to be able to do, the kind of things that the ecologists would like to be able to do, is to detect things like kind of species presence, absence, species richness, biodiversity, behavioural studies, and overall environmental health management. Management's what happens after measurement. It's kind of interesting that if you look at this from a sort of sensors perspective, and I'm kind of an IT guy, so this will appeal to me. If you look at a lot of the sort of traditional work that's being done with sort of wireless sensor networks and things, they really tend to be sort of focused on the sort of first three ecological sort of processes. The fourth sort of process concerns sort of biodiversity and species relationships. You really need people to do that, or at least you've got to sort of emulate the sort of scientist's sort of eyes and ears, which is what we're trying to do. You can also do some sort of high-level vegetation assessment and things from using sort of remote sensing, and potentially using kind of UAVs and that kind of thing. But for the detailed stuff, you actually need kind of people on the ground. Sound is sound sort of an interesting thing to work with. There are a lot of benefits to sound. It is, in general terms, tractable. It's a tractable medium compared with trying to do automated analysis of image data or videos and things. You can do a lot more with sound. Sound is sort of wide-ranging. It obviously sort of carries quite a long way. Although again, it is necessary to sort of understand the characteristics of sound and why it's being used. Obviously, sound is being used by fauna to communicate. So depending upon the actual behaviour of the animals, that's going to determine the kind of sound they use and how they use it, because they're using it for communication. So for example, some animals use things like very low frequency sound, infrasound, because it can kind of carry sort of long distance. Some animals use a mixture of different kinds of sounds for communication. There's been obviously a lot of research into sort of human speech recognition, a lot of research dollars sort of poured into that. Unfortunately, conversely, there's not been so much work that's been done on terrestrial acoustics. A lot of work's been done on marine acoustics. With sound, potentially you can do quite a lot with it. You can obviously do, hopefully you can do things like distinguish some species. If you use sort of array microphones and things, you can distinguish sort of location. Potentially you can tell a bit about the behaviour of fauna. And with some fauna, it's even possible to sort of recognise, at least theoretically, individuals. There are other sounds of interest. So, interestingly, compared with sort of traditional speech processing and things, there's not a lot of really so-called noise. Most of the data that's actually coming into the microphone we're interested in, even if it's wind, that's useful to know. It tells us something about the climate. And you can actually use sound as a way of sort of gauging kind of the amount of rainfall. There's even things like kind of soil probes and the like, which often are essentially sort of microphones. They can sort of gauge soil humidity based on the sound that it makes. The challenges with sound and things, obviously, it's sort of it's very sort of voluminous, it's processing intensive. Not all fauna makes a sound, so you can't detect everything with it. So it has an inherent sort of bias. So the set of observations you're going to get from sound are going to be different from those that the ecologist would normally make. And there's an awful lot of sort of variation. So there's a sort of a spectrogram up here, which is, if you like, a frequency graph, frequency over time. There's a lot of different events and things occurring there. We want to be able to sort of pull that apart to determine what's going on. Because of the nature of sound, because of the sort of issues of noise, because you get these sort of overlapping events, because of the variations and things, we sort of strongly believe that we're going to need human-in-the-loop style systems. So we're going to have a huge volume of sound. Think about something like an MP3, you're talking about, you know, a megabyte a minute, just from one sort of sensor continuously sensing, you're going to get a gigabyte a day. So you can collect a lot of data this way. So it is eScience. We end up with, we haven't got a lot of sensors, but we've certainly got at least a sort of terabyte of data sitting in our database. In order to analyse that, we actually need some kind of automated systems to help, but we believe we're going to need sort of human-in-the-loop style systems. The approach we're taking is certainly inspired by Jim Gray. We're trying to be focused on the scientists, on the questions that they want to ask of the data. We're moving from one working system to another, which can be sort of challenging, so we are trying to adopt a pretty agile approach. We're very pragmatic, we're very low-fi, so we're interested in using kind of commodity, cheap, recording MP3 player type of technology so that we can get the scale. We're interested in getting a lot of observations. We believe we're going to need a toolbox, that there's going to be no single approach that's going to work for analysing the sound, so we've developed a sort of a toolbox of technologies and we're sort of adding more to that. And also I guess sort of there's this fundamental issue that what we're trying to do is to trade sampling or sensing time for detection accuracy. So if you actually look at the sort of the models that the ecologists have when they go out and take observations, they're assuming that they're 100% accurate in sort of sensing anything that's there once they're actually there. So we may not get that with our sensors or with our sort of recordings in terms of all the way in which we can analyse the sound, but what we're hoping, I guess, what we're sort of trading off is that because we can kind of sense for longer, for sort of 24/7 and throughout the environment, that we can trade that and therefore get the sort of detection that we need. The kind of questions that we have, the sort of simple questions are just a certain species present, when are species active, what species are there, how is the environment changing, and ultimately some idea of sort of environmental health. Obviously some of those are kind of quite difficult questions, and we haven't got this is only 5 questions, not the 20 or so that Jim was sort of proposing, but that's at least a sort of start for us. In terms of our analyses approaches, having said that we actually need to automatically analyse or semi-automatically analyse the data, the scientists generally do want to go back and check the data. The scientists who are actually interested in animal sort of behaviour actually want to sort of listen to the data, they actually want to listen to the sound to sort of get an idea of what's sort of going on. One thing that's interesting is we're very good at visual processing and less good at sort of auditory sort of processing. So often what our scientists will do is to visually scan spectrograms, and you actually can scan them pretty quickly. And there are actually other groups that are actually using this as a real on-the-ground technique. They're actually just visually sort of scanning spectrograms to sort of find calls of interest. From an automated approach, we've investigated at least sort of 3 different things, which I'll talk briefly about. A more classical sort of speech recognition approach using sort of HTK. It's a template-based recognizer where you've got a particular recognizer to recognise a particular kind of call. We're also using some image processing approaches to look for particular kinds of acoustic events, in a way trying to sort of emulate the sort of image-based scanning that the scientists do. And also we're attempting a kind of a whole of soundscape approach, doing a kind of an energy style analysis of the whole spectrograms. So the first approach which we have is the automated speech processing one. It's really just using sort of standard speech processing technology. It means that you have to have a template tuned based on a lot of training data to a particular call type. It works reasonably well for some calls, so particularly for birds with sort of very well-defined whistles, where you've got reasonably clean sound, where you've not got a lot of overlapping events, it can work quite well. So we've successfully used it in some environments. There's obviously a lot of work and research has been poured into speech recognition, at least speech recognition for English anyway, and it tends to be a very sort of constrained problem. The problem with the natural sound is it's very unconstrained. You get a lot of variation, but depending upon the weather, depending upon the season, depending upon the species, the calls evolve over time, they're different in different places, it's sort of really hard. So it doesn't work well for everything. You can't just say, okay, we'll use speech recognition technology. Won't work well enough. Second approach which we've tried is to sort of do image processing on the spectrogram, so not actually on the JPEG, the spectrogram, but actually on the sort of spectrogram data. That works sort of quite well. Again, there are different ways that you can do that. The spectral peak tracking is a common way. We haven't actually done that yet, but we've actually got another way which works better for the kind of calls which we have, because we are driven by what the scientists are trying to do. Kind of thing, it doesn't show that well, but there's a spectrogram underneath that, but this is sort of picking out various events in this case, the particular event that we're interested in is this one here. This is actually a ground parrot, which is a rare species. It's an indicator species, so it's a good indicator of environmental health. And as you can see, that's quite a difficult thing. We've got other overlapping events, for example, here. It's quite a difficult thing to recognise. So we have, using this sort of event detection approach, we've then on top of that come up with a way of sort of framing these events, counting events and looking for particular patterns, and we've actually been able to get a reasonable level of accuracy for detecting these sort of ground parrots. So this is the other good thing about this approach is you don't need a lot of training data. Again, in automated speech recognition, if you've got a group involved in that, one of the first things you do is you buy these sort of huge databases containing kind of marked up speech and the like that you use for training and things. We don't have that, or it's hard to get in this case. You can get it potentially from some sort of citizen science-like approach, but yeah, we're not there yet. And as I say, there's an awful lot of, sort of variation in the calls and things anyway. So we're able to distinguish these calls. We're able to distinguish there's actually two calls here because these parrots are actually calling to one another. So there's one call here and another call here. We've also been able to use it on our kind of koala calls, which we're trying to recognise as well, which again are not amenable to the classic sort of speech recognition style approaches. The third approach which we've tried is one where we're trying to look at the overall sort of acoustic landscape. Some sort of, we wondered, is there some holistic way at looking at the environment? It's kind of motivated by information theory, I suppose, in that if you think about it, the animals are making noises in order to communicate. So you kind of think you ought to somehow be able to appeal to sort of Shannon's sort of information theory to look at the amount of signal that there is in the environment to get some idea of what's going on. It's different from other kind of noise. It's not white noise, right? So we've started doing that. We've tried it using sort of energy. We've tried it using our sort of acoustic events and just being able to get some idea of average kind of events that are occurring within particular kind of frequency bands and things. And essentially what we want to do is try to correlate the sort of the patterns and the richness of these events with the sort of the biocondition, with the sort of the health of the environment. I can't claim that we've actually achieved anything there yet. Maybe we need a greater level of information, a greater sort of detail of information to make that work. But I think it's a promising approach. I'll briefly sort of skip through some of these slides now. In terms of architecture and things and how you actually kind of collect sound and do this kind of stuff, there are sort of different approaches. Sometimes it's really hard and you don't have any networking or anything, so essentially you've got to put out some sort of glorified tape recorders, and then you've got to kind of just sort of manually collect those. They're just sort of logging and kind of upload the data. It's possible to do sort of sound streaming. The problem with that is you need quite high bandwidth if you're going to stream a lot of data. An alternative to that, if you've perhaps a more scalable approach, is where you actually do some of the recognition analysis actually on the device, on the sensor. That way you've got less data to sort of stream around. The problem with that is if you don't store the data, you can't go back to it. You can't then sort of retune and things. So in general, our approach is we want to keep the data. So we've got a very centralised architecture. Works okay for us at the moment. I still don't know. It's an open question in my mind of whether we're actually going to be able to get the scalability, because this is a kind of extremely sort of high fan-in style system. One of the cool things which we have to do with our system is we actually offload the analysis jobs to a cluster computer on the back end, because they're quite intensive and we need to do quite a lot of them. So that's actually a sort of Windows sort of HPC server. We have a web interface for sort of managing our sensors, for undertaking the analysis, for sort of tagging. This web. I'll skip through this quickly because I'm going to do a very, very brief demo. We've got a website that enables users to sort of do stuff. We've used some sort of interesting technology, so we've used sort of Silverlight. We've got some F# for our analysis code. We use Virtual Earth. We use SQL Server. The whole kit and caboodle. We've done some work with a rare cryptic bird at Brisbane Airport, which is very difficult to study for a whole variety of reasons, including snakes and difficulty of getting access to the airport, because it's obviously controlled, and a whole bunch of things. That's been very successful. We've got a test site where we're looking at our sort of overall health of the environment style sort of work, which It contains a number of different little ecological kind of areas which are of interest to the ecologists. And we've been doing some work on koalas at St Bees, which if you were here last year, I played some koala calls, and I'll do that briefly again today. So in conclusion, we've researched and deployed a system. It's in day-to-day use. It's enabling sort of new science. We've tried to follow sort of some Jim Gray's kind of ideas. We have sort of discovered things, so we've sort of made the scientists happy. They've been able to sort of publish papers. There are still big questions because ecologists are very tied to particular protocols and methods, and rightly so. So there's still a great deal of need for people that can kind of span the two areas to actually sort of test these techniques and understand the inherent biases of the techniques of using just sort of sound in these automated systems. Okay, let me do some quick thanks and then a very, very quick demo. Yes, I'd certainly like to thank Microsoft Research for their support, for inviting me here, and the state government, Brisbane Airport, Telstra, and San Diego Zoo for their help and support. I'd like to put in a couple of plugs for the IEEE Science Conferences. I'm PC Chair for this year's one, which is in Oxford. Next year's one's going to be in Brisbane, Australia. Please come and visit. It's a great place. Okay, so let me just show you. Whoops, that's spam. So this is our website. This is the sort of the data page. What I've actually done here is I've done a quick query. This is actually a call from one of our sensors on an island, sort of in the Barrier Reef, I guess, where there's been an isolated population of koalas. They weren't there naturally. They were sort of put there. There are some ecologists studying these koalas. They want to understand about their calling patterns and behaviour, because the koalas are basically a great risk of becoming kind of extinct, or at least extinct outside kind of captivity. So there's a need to understand their calling in the wild. They still don't fully understand why koalas call, and also it's going to sort of help obviously sort of breeding and their and looking after them in sort of captivity. So this was one of the ecologists who I work with who's studying koalas. He actually tends to manually, although we have actually got some tools now to help him, but he tends to sort of manually just listen to these recordings. He just sort of leaves them playing at home. When he hears a koala, he then actually goes and tags them up. So I'll play you a koala and then stop. So you can see this is our Silverlight player. This is the sort of spectrogram. This was from 1 o'clock. So the koalas call, well, they don't always just call it dawn and dusk, which is what was previously sort of thought. This is a marked up koala call. That's a koala call. Very strange sound. Yeah, it's a sort of huffing and puffing. But it's interesting, you can kind of see the events, right? And so we're obviously trying to sort of pick out these events. It's not going to be precise, but you can kind of get an idea that some image processing style techniques ought to work. And this is sort of a marked up area, so you can kind of just draw little tag little sort of areas on this. Okay, I'll stop there so there's time for some questions. Thank you.
Any questions?
Ecological questions usually have a long time span of getting into the problem and then getting into a solution.
Mm-hmm.
Are there any historical records of sound that you can go to and reanalyze?
Oh, that's a good question. I hadn't thought of that. I don't know, to be honest. I hadn't thought of that.
Airports have sensors for noise.
Yeah.
It's just like decibels and not the spectrum.
Absolutely, yeah. I mean, in some ways, I think some of this is only just becoming possible because of iPods and things, basically. Some of this is only just becoming possible that we can get these very cheap bits of technology just to, do kind of continuous recording and things because of the, consumers. I'm not aware if there is any other historical sounds, but you're right that there's sort of long-term and sort of short-term monitoring. We're still sort of playing around with the technology, but I think the goal would actually be to have some sort of long-term monitoring of the sounds. Yeah, there are some. I'm aware that for example, we ran a workshop which was part of Intercol earlier this year, and certainly in New Zealand they've got a project now where they're actually going to have rangers going into the national parks and deploying some little sort of acoustic loggers, and they're particularly concerned about kiwi birds, but they want to keep all of the data, so all the sound is going to be recorded on these little couple of $100 devices to an SD card. They're going to keep all the data with the idea that in the future they ought to be able to mine it for other information.
How far apart do you need to keep the sensors to keep from correlating the same sound with the two sensors?
Well, that's a good question. Again, it depends on the environment. It depends very, very much on the environment. If you've got a relatively sort of open meadow or something like that, and if you're looking at kind of birds and they're flying around, the sound is likely to carry quite a long way, and deliberately so. I mean, I'm not an ecologist, but if the sound carries a long way, it's because the animals want to communicate a long way, not a long sort of distance. Obviously, if you're in a dense forest or something, the sound tends to carry much less far. But again, it's attenuated based on frequency and things. So I think it's sort of elephants have discovered use of infrasound for quite long-range communication. I think there are other species that do similar things. I'm not an ecologist, so I tend to I go to the ecologist for those kind of questions. They usually don't know.
It seems like you'd have to look at data samples with each other after a while in order to parse out events that carry a long way.
Yeah, I mean, the ecologists actually do surveys at the moment, and they sort of sit there and do bird counts and things like that. So we're trying to. I have a student who's actually working with the ecologist, and he's actually sort of following them around basically, and seeing what they do, and he's taking recordings at the same time as they're doing their their sort of human observations, and we're trying to correlate the two.
How many species do you have the spectral signature for in terms of
Not many in truth, probably about a dozen or so. Part of the reason is that we're still trying to sort of tune them and work on what the right approaches are. And we're also driven by, some ecologists are obviously interested in a particular particular species. So for example, the Lewin's railbird makes 4 types of calls, and we've got recognizers for 2 of them. Whereas other ecologists, like Dr. Ellis, who's interested in the koalas, is actually interested in one species. He's actually interested in the particular behaviour. So he's actually listening to call. He actually wants to understand why they're calling and when they start calling and things like that. That's different. He knows the koalas are there, and he really knows they're there because they've got GPS tracking collars on them. But he wants to understand why they're calling. I mean, I think that my goal and motivation really is that I'm interested more in the sort of whole of this whole of environment sort of assessment, so some of these sort of biocondition metrics. But you've got to start obviously with some sort of particular species and then generalise from there. I mean, trying to analyse sort of sound in the general sense like this is a really hard problem.
Time for one more, perhaps? Tom?
It's clear that a human in the loop is really essential right now.
Yeah.
Are you anticipating the capability of the technology to progress to the point where this could be more automated?
No. I think. I think there will always be a human in the loop. It's a question of degrees, really. We know that the sounds sort of evolve over time and things, and most scientists want to go back and verify the data. And I think you're going to need to do that. I mean, you get all sorts of things happening. You get crickets that sit on top of the microphones. The microphones can become damaged and things. So I see the goal as making it tractable. Saying if you've got these sort of weeks, months, years worth of data, how can you use a few hours, days of scientist time to be able to analyse all of this data?
So I had a follow-up. So it is possible that you are able to, for example, this marked region. Today that's manually marked.
Today that's manually marked. We can.
It is possible to at least get some candidate regions to.
Absolutely, yeah.
Yeah. So that's where you're headed.
Yes.
Not
yes.
there yet.
Well, we have got I'm not sure I've got it here, but we have got started an interface for some of that. So there is. It's a bit slow. There is some of that online at the moment. I don't know if there's any at St. Bees. Look at the jobs. So I can sort of drill down and see. We have some of it online. It sort of ongoing. So
Great. Thanks again, Paul.
thank you.